In a workshop in Cleveland, late autumn 1918, retired Army Colonel John Taliaferro Thompson stands over a wooden bench crowded with springs, steel components, and machined receivers. The air carries the scent of oil and metal shavings. Light from high windows stretches across blueprints pinned to the wall, each one marked with revisions in pencil. Before him rests a prototype, compact, heavy, built around a principle he believes will change everything. The great global conflict still rages in Europe, though telegraph reports arrive daily, suggesting its approaching end. Thompson adjusts a small bronze wedge inside the equipment's bolt assembly, testing the resistance with his thumb. This component, no larger than a domino, represents years of theoretical work. He believes it is the key to controlling automatic fire in a package light enough for one person to carry. Theodore Eickhoff, the project's chief machinist, watches from across the room. He has built what Thompson specified, but privately he wonders if the bronze wedge matters as much as the colonel insists. The prototype has functioned successfully in controlled tests, cycling through magazines with mechanical regularity. Yet Thompson remains obsessed with this small triangular piece, explaining again how friction between dissimilar metals will delay the bolt opening just long enough for chamber pressure to drop. Eickhoff nods, says nothing. He has learned that engineers and inventors often pursue ideas with a certainty that outpaces evidence. Thompson lifts the device, feeling its weight, nearly 11 pounds unloaded. The barrel is finned for cooling. The buttstock, cut from American walnut, sits low and straight. A vertical foregrip extends forward beneath the barrel, positioned where instinct suggests a hand would naturally brace against recoil. Everything is deliberate. Everything is calculated. Yet the project has consumed more money and time than anyone expected, and the struggle it was designed for may end before production begins. On the bench beside the prototype lies a stack of correspondence from the department, polite, non-committal, expressing interest without commitment. Thompson rereads one letter, then sets it aside. He knows what they are thinking. The design is expensive, complicated, unproven. They want standard rifles, artillery, conventional solutions. They do not yet understand that the nature of engagement is changing, that the next major confrontation will demand something between a sidearm and a rifle, something that delivers sustained fire at close range without the burden of belt-fed systems or water-cooled barrels. He believes this. He has staked his reputation and fortune on it. Outside, the first snow of the season begins to fall. Thompson returns the prototype to the bench, picks up a small file, and begins smoothing an edge on the receiver. The work continues. Somewhere in his mind, he knows the hostilities may end before this equipment reaches the field. But the principle, he tells himself, will endure. The principle must endure. If stories like this help you see how engineering quietly shaped history, tell us in the comments what surprised you so far, and stay with us for the next chapter. Buddhist John Taliaferro Thompson was born in Kentucky in 1860, the son of a high-ranking officer who served during the domestic conflict. He grew up surrounded by traditions and mechanical curiosity, qualities that led him to West Point and then to a career in ordnance. For years, he worked on improving equipment and small systems, observing how industrial production could meet large-scale needs. He saw the Spanish-American era, watched the evolution of automatic tools, and understood that power was becoming concentrated, mechanized, and decisive. By 1914, he had retired from active service to pursue private ventures in manufacturing. Convinced that the next major event would demand innovations, the establishment was too slow to develop. The great global conflict confirmed his instincts. Reports from Europe described trench systems, close-quarters encounters, and the desperate need for portable automatic equipment. The standard infantry rifle, bolt action, accurate at range, proved inadequate in the mud and chaos of the front lines. Personnel needed something that could deliver multiple rounds rapidly without requiring crew operation or fixed positioning. Thompson saw the gap and believed he could fill it. His partnership with Commander John Bell Blish began in 1915. Blish, a naval officer with a background in metallurgy, had observed unusual adhesion properties in heavy equipment breech blocks during testing. He theorized that under high pressure, certain dissimilar metals would exhibit increased friction, enough, he believed, to delay a bolt opening without requiring a mechanically locked breech. Thompson seized on this idea. If Blish's principle held true, it would allow a compact automatic tool to remain lightweight while safely utilizing powerful cartridges at automatic rates. The theory was elegant, the mathematics compelling, and the potential transformative. They formed the Auto Ordnance Corporation in 1916, raising capital from investors who believed in Thompson's vision and reputation. The goal was clear: design and produce a submachine gun using the Blish lock principle, deliver it to the authorities before the hostilities ended, and establish a new category of infantry equipment. Thompson recruited engineers and machinists, rented workshop space, and began translating theory into steel and bronze. But theory resisted translation. Early prototypes jammed, overheated, or cycled inconsistently. The Blish lock required precise machining. The bronze wedge had to fit exactly between bolt and receiver, maintaining contact under pressure while releasing smoothly during recoil. Any variation in tolerances caused a failure. Thompson pushed his team to refine measurements, adjust spring tensions, and test material combinations. Months passed, costs mounted, investors grew anxious. The department observed from a distance, polite but uncommitted. By late 1918, Thompson had a working prototype, but time was running out. The conclusion of the struggle seemed imminent. If the equipment didn't prove itself soon, the interest would vanish, and the entire venture would collapse. Thompson knew this. He also knew that the principle, the friction lock, the differential adhesion Blish had theorized, was either correct or it wasn't. And if it wasn't, everything he had built would rest on a foundation of misunderstood physics. The Thompson submachine gun operates on what its creator called the Blish lock system, a delayed blowback mechanism built around the belief that dissimilar metals under high pressure create measurable resistance through differential friction. The concept was straightforward in principle. When the tool fired a 45 ACP cartridge, the expanding gases drove the projectile forward and pushed the bolt rearward. At the same moment, a bronze wedge, the Blish lock component, positioned between the bolt face and the receiver's interior surface, would lock momentarily due to friction, holding the breech closed long enough for chamber pressure to drop to safe levels. Only when pressure subsided would the friction release, allowing the bolt to continue its rearward travel, extract the spent casing, compress the recoil spring, and then return forward to chamber the next round from the magazine. Thompson explained this mechanism repeatedly to observers, engineers, and potential investors. He demonstrated how the bronze wedge, precisely angled and machined, created a temporary mechanical advantage without adding the weight and complexity of a rotating bolt or tilting barrel. The system, he argued, allowed the tool to fire 600 to 700 rounds per minute, while remaining light enough for one person to carry and operate effectively. The 45 ACP cartridge, the same round used in the M1911 sidearm, provided stopping power without requiring rifle-caliber pressures that would demand heavier construction. The engineering challenge was integration. The design needed to balance competing demands: compact size for maneuverability, sufficient weight to absorb recoil, simple enough for field maintenance, robust enough for harsh conditions. Thompson's team designed a finned barrel to dissipate heat during sustained fire, a removable barrel assembly for cleaning and replacement, and a vertical foregrip positioned forward to counteract upward movement. The buttstock, cut from walnut, was straight and low to align the barrel axis with the operator's shoulder. Every dimension represented a calculated compromise between portability and control. Yet when Thompson presented the equipment to evaluators in early 1919, their reception was cautious. They acknowledged the mechanical ingenuity, but questioned the necessity. The hostilities had ended. The immediate need had passed. More fundamentally, they weren't convinced the Blish lock contributed what Thompson claimed. Some evaluators suspected the equipment worked primarily through simple blowback, that the bolt's mass and the recoil spring's resistance were sufficient to delay opening, making the bronze wedge redundant. Thompson countered with Blish's metallurgical data, insisting the friction principle was measurable and essential. The resistance wasn't hostile, merely skeptical. Procurement favored proven designs, incremental improvements, and cost efficiency. Thompson's tool was expensive to manufacture, required precise machining, and introduced a theoretical component that couldn't be easily verified in field conditions. Evaluators asked pointed questions. Could the equipment function without the Blish lock? Had Thompson tested a simplified version? What evidence proved the wedge was necessary beyond theoretical models? Thompson deflected. He believed in the principle with a certainty that made doubt seem like misunderstanding. The equipment worked. The tests proved it. The mechanism as designed delivered the performance he had promised. Whether the Blish lock was essential or incidental seemed to him a question that missed the larger achievement. Do you think this design choice was inevitable or a risky gamble at the time? Share your view in the comments and pass this story to someone who enjoys understanding how things really work. Testing continued through 1919 and into 1920, even as official interest cooled. Thompson arranged demonstrations at ranges outside Cleveland, cycling thousands of rounds through multiple prototypes to prove reliability. Engineers recorded cycle rates, measured barrel temperatures, and documented malfunctions. The equipment performed well under controlled conditions, but field tests revealed problems. Mud infiltrated the action, fouling the bronze wedge's surface and causing erratic cycling. Extreme cold stiffened lubricants, increasing friction beyond calculated tolerances. The drum magazines, distinctive 50 and 100-round cylinders, were heavy, expensive to produce, and prone to spring fatigue. Theodore Eickhoff proposed modifications. Simplify the bolt assembly, increase clearances to accommodate debris, replace the bronze wedge with a simpler delay mechanism. Thompson resisted. Each suggestion felt like an admission that the original principle was flawed. He authorized minor adjustments, improved seals, stronger magazine springs, refined metallurgy for the wedge, but refused to abandon the Blish lock. The design, he insisted, worked because of the friction delay, not in spite of it. Meanwhile, Auto Ordnance struggled financially. Production costs exceeded projections. The authorities showed no inclination to place orders. Investors demanded results. Thompson needed a market, but the peacetime era wasn't buying experimental equipment. He pivoted, marketing the Thompson submachine gun to law enforcement and private security firms. Advertisements emphasized stopping power, rapid fire, and American engineering. The equipment found limited adoption. Some departments, a few private security companies, and industrial operations in remote areas. Sales covered costs, but didn't justify the investment. Then came an unexpected consequence. The same features that made the Thompson formidable in theory made it attractive to those operating outside legal structures. During the era of prohibition, organized groups discovered that a compact automatic tool firing .45 ACP rounds could overcome numerical disadvantages and intimidate rivals. The Thompson's reliability, magazine capacity, and portability suited contexts Thompson never intended. Newspapers began associating the equipment with incidents in urban settings, eroding its reputation among legitimate buyers. Thompson watched his creation become notorious rather than celebrated. He had designed the tool for service personnel, for trench use, and for national defense. Instead, it became a symbol of disorder. The engineering achievement, the Blish lock, the integrated design, the careful balance of performance and portability disappeared beneath sensational headlines. He continued to defend the principle, to explain the friction mechanism, and to insist that the equipment worked exactly as intended. But the public and the press weren't interested in metallurgical theory. They saw the outcomes, not the principles. Auto ordnance persisted, producing models in small batches, refining manufacturing processes, and waiting for the market to shift. Thompson remained convinced that eventually the military would recognize what he had created. The equipment worked. The principle was sound. Time, he believed, would prove him correct. By the mid-1920s, engineers outside auto ordnance had begun examining the Thompson design with fresh perspective. Some acquired decommissioned models, others worked from technical drawings circulated through official channels. Their analyses reached a consistent conclusion. The Blish lock contributed almost nothing to the tool's function. Tests demonstrated that removing the bronze wedge entirely had negligible effect on cycling rate, reliability, or pressure management. The system worked primarily as a simple blowback design. The bolt's mass and the recoil spring's resistance were sufficient to delay opening until chamber pressure subsided. The friction principle Thompson had championed was mechanically insignificant. This revelation didn't invalidate the equipment. It simply meant that Thompson had succeeded for partially different reasons than he understood. The careful weight distribution, the spring calibration, the material selection. These elements combined to create a functional automatic tool. The Blish lock was an elegant addition that added cost and complexity without contributing to performance. Later manufacturers would design simplified versions without the wedge, and these functioned identically to Thompson's original. Thompson himself never fully accepted this conclusion. Even as evidence accumulated, he maintained that the friction principle was real, measurable, and essential. His conviction wasn't dishonest. It was the natural resistance of an inventor whose theoretical foundation proved unnecessary, but whose practical achievement remained valid. The equipment worked. Personnel would eventually use it. The principle, he believed, must therefore be sound. The second global struggle of the century vindicated the concept of the submachine gun, even if Thompson's specific friction theory remained unproven. The tool saw extensive service in multiple regions, valued for exactly the qualities Thompson had emphasized: portability, rapid fire, and reliability in harsh conditions. The later M1 and M1A1 variants eliminated the Blish lock and the finned barrel, simplifying production without sacrificing performance. The equipment Thompson had built around a misunderstood principle became a standard tool precisely because the other engineering decisions, the ones he had made almost instinctively, were correct. The final curiosity, then, is this. Thompson created a design that worked for reasons he didn't fully understand, built around a principle that wasn't necessary. The Blish lock was a technological artifact of misapplied physics, a component that added weight and expense without contributing to function. Yet the equipment surrounding it represented genuine insight. Thompson understood that personnel needed something between a sidearm and a rifle, something that could deliver sustained fire at close range without the limitations of crew-served systems. That understanding, not the bronze wedge, was the innovation that mattered. John Thompson passed away in 1940, just as the equipment bearing his name was entering full production for a global struggle he had not anticipated. He never saw the Thompson submachine gun deployed on the scale he had once imagined, never witnessed its adoption by forces worldwide, and never received the official validation he had spent decades pursuing. But his creation persisted, evolving beyond his original vision into something both simpler and more versatile than the Cleveland prototype with its meticulously machined bronze wedge. The engineering legacy of the Thompson is complex. On one hand, it demonstrated that deeply held theoretical beliefs can coexist with functional success, that an inventor can be wrong about why something works while still creating something that works well. On the other, it established foundational principles for automatic design that later engineers would refine and improve. Blowback operation, specific ammunition choices, select fire capability, and forward grips for control. These elements became standard, not because Thompson understood friction dynamics, but because he understood the operational gap between existing tools. The Blish lock itself faded from design history, remembered primarily as a historical curiosity. Modern engineers studying the Thompson treat it as a lesson in the difference between theoretical elegance and mechanical necessity. The principle Thompson championed, differential friction between dissimilar metals under pressure, wasn't incorrect in absolute terms, but it was irrelevant to this application. The forces involved were too brief, the pressures too high, and the tolerances too variable for the effect to matter. The equipment succeeded because Thompson's practical engineering instincts outweighed his theoretical assumptions. What remains is a study in conviction meeting complexity. Thompson believed so completely in the Blish lock that he never seriously considered testing the equipment without it. His certainty shaped every decision, every refinement, and every explanation to skeptical evaluators. That same certainty made him resistant to evidence suggesting the principle was unnecessary. He finished his journey believing he had harnessed a fundamental physical property, when in fact he had simply built a well-balanced blowback tool around an elegant but superfluous component. Perhaps that's the deeper insight. Innovation rarely follows the clean paths inventors imagine. Thompson set out to prove a metallurgical theory and ended up creating a practical tool that worked for different reasons. His legacy isn't the Blish lock. It's the understanding that certain types of engagement required portable automatic fire and that such equipment could be engineered with existing materials and manufacturing techniques. The bronze wedge was his explanation. The equipment itself was his achievement. The Thompson submachine gun remains in museums, films, and history, a symbol of an era and a reminder that engineering success sometimes emerges from the space between theory and practice. Thompson's conviction gave the project momentum. His misunderstanding of the mechanism didn't prevent the equipment from functioning. And in the end, the question of why it worked mattered less than the fact that it did. If you enjoy calm, true stories about how engineering shaped the world, subscribe to the channel, leave a like, and tell us from which country you're watching.